Hello everyone, it's Mahin. So in this video, I'll talk about a very powerful integration technique called integration by substitution, which is probably the most widely used integration techniques out there. Most of the integral problem that you will face can probably be solved by using this technique. Okay, so this is basically the underlying theorem of the integration by substitution technique. Now, you don't have to really know the proof of this theorem. I'm not going to prove it here. The proof is not very difficult though. You have to know some basic ideas like fundamental theorem of calculus, but I'm not going to prove it here because the goal of this video is to just show you how you can apply this technique in solving practical integral problems. Okay, so I'm going to explain the theorem here. So let's say if we have a function of this form, let's say we have an integral, let's say we have an integral of this form. So of the form of f of g of x multiplied by g prime x, which is basically means the derivative of gx. G prime x means derivative of gx. So if we have an integral which we can express as in this form, then according to this theorem, according to the underlying theorem of integration by substitution technique, we can write it as like this. So what we are basically doing here is that we are substituting u for gx here, right? So what we are doing here, let's say we are substituting u for gx. So basically we are saying that okay, let gx be u, gx be equal to u. So if we substitute gx with u, and then what will be the situation of this part? So let's say if we substitute gx with u, then we'll have if we take derivative of both sides here, we'll have g derivative x, and this side will have ddx of u, and we can write it as like du equals to g prime x multiplied by dx. So basically it's equal to d is equal to this side of the integral, right? This side of this function. So we can substitute. Basically what we did here, we substituted we substitute gx with u, and then we substituted g prime x dx with du, right? That's basically what we did. So, and also another thing that we did is that we substitute gb with b with gb and a with ga. So let me write down all the substitution that we did here in the theorem. So we are substituting gx with u. We are substituting g prime x dx with du. I mean, you can see why you are substituting here. I just already showed it to you. And then we are substituting b with g of b, and we are substituting a with g of a, right? So that's basically the idea. So if we do that, then we can convert this integral to this integral, which will be simpler version of the integral. So the goal here is to, if we have a very complex function which of this form, of this structure, we can convert it to the simpler form, and so that maybe we can convert it to a standard form of integral that we already know the integration of by heart, and we can solve it by that way. So if you didn't know that there is actually standard list of standard form of integral, if you didn't, I'm gonna put a screenshot here so that you can have a look at it. You should memorize this list by heart. I mean, obviously there's the explanation. I mean, you are getting this list directly from differentiation technique. We're just reversing it. So our goal is to convert this. If you have a very tricky integral of this form, we are going to convert it to this form, so that our goal is to convert to standard form so that we can solve it easily. Okay, so I'm going to show you some example, first-hand example, like how we can apply it in practical problem. So the first problem that we have here is that we have to find the definite integral of cos x multiplied by sine cube x dx, and the limit is from 0 to pi by 2, right? Now when you see this function, right over here, integrand, we call it integrand, we'll try to convert it to of that form. What is the form? The form was f of g of x multiplied by derivative of gx and then dx, right? Okay, dx is obviously part of the integral. So this form, I'll try to convert it to this form. Can we do this? Well, the trick here is to realize that the derivative of sine x is actually cos x, right? So we have sine function here, cos function here. Then that means we can do something about it. So let's assume sine x to be u, and then we're going to take a derivative of it. We're going to put, what will be the derivative? Well, derivative of sine x is cos x, of course, and the derivative of the du is like du dx. And then we're going to take dx here. We're going to have du. I mean, we cannot do it, we cannot consider it to be a fraction, so it's not like I'm basically multiplying both sides by dx. It doesn't work that way, we know that, but we can still write it like this. There's a proof of it, like why we can, you know, do it like this. We can write it like du and then cos x dx. But I just wanted to make sure, I just wanted to emphasize here, du dx is not a function actually. This is not a function. Sorry, this is not a fraction. This is not a fraction. This is an operator. Okay, I just wanted to emphasize here. This is not really a fraction, so don't consider it to be a fraction. It's an operator. But still, we know that we can write it like this. Now, if we do that, then we can substitute. So basically, what you got here is that du is equal to cos x dx equal to du and equal to sin x. So what you got, we can substitute sin x with u, right? First, instead of sin x, we're going to write u, and then instead of cos x dx, we're going to write du. So we're going to do it here. Instead of sin x, we're going to write u. So we'll have u cube here, right? U cube, and instead of cos x dx, we can write du. Cos x ds overall, it will be du, and then integrals. But there is this catch here, is that we have initially in the original problem we had, it was limit was like from 0 to pi by 2, but we know that we also have to substitute them. So in the theorem, the theorem that I wiped up already, we saw that we have to substitute a with g of a and b with g of b, right? So here our a is, let's say, 0. So for what is, if a is 0, for 0 we can substitute 0 with g of 0. What is g of 0? Well, what is g of 0? G was, we assume g to be sin x, right? Sin x equal to sin x is basically g, so, or u. So what we're going to do is that we're going to write g of 0 is equal to u, which basically means is that sin 0 equal to 0, and then for pi by 2 we can substitute pi by 2 with again g of pi by 2 or sin pi by 2, and which is equals to 1. So you substitute pi by 2 with 1 and 0 with 0. So the limit here of this substituted integral of this, you know, formulated integral, it will be, here it will be 0, it will be 1. And what is the integration of u cube? Well, it is basically, we know from the standard, we know that there is a standard form of integral that we know by heart, is that if we have something like n cube, we have equal to n power 4 by 4 plus c, right? We know this formula, so I'm going to use that formula here. So we'll have u power 4 by 4, and then I'm going to solve the definite integral. I'm going to put the true limit. It will be 1 power 4 by 4, and here 0 power 4 by 4, which equals to, if we calculate, it will be 1 over 4, which is the answer. Now let's have a look at a different problem. Now let's have a look at this problem right over here. Now the first thing that you may notice is that there is no limit over the integral sign, over and under the integral sign. That means basically it's an indefinite integral. Now some of you may wonder, well, how can we apply this theorem or this technique in indefinite integral? But actually it's possible. It's very much possible also on the indefinite integral. The idea is that if we can apply it on a definite integral that is that is valid and that is that is continuous and bounded in the interval a and b, then it's also valid for an indefinite integral that is bound and continuous in some kind of interval, right? So it's equally valid for indefinite integral. So I'm going to show you how to apply this technique for an indefinite integral. All right. So again, we have to assume the tricky part of the solving this kind of problem is that choosing what to assume as u, what to substitute with u. So in this case, we're going to substitute, let's say 1 plus x as u. Let's say let u be 1 plus x, right? Then we have to find now the remaining part. So what will be du if we take an integration here? If we differentiate both sides, we'll have du dx here. On this side, we'll have this part will be 0 and this part will be, which is 1. That means we have du dx equals 1. That means du is equal to dx. They are equal. Dx and du are equal, right? So what we can do right over here is that we can write so we can substitute these things here in the original integral. So for 1 plus x we have u power 100, and what we're going to write for x squared, well, we assume that u equal 1 plus x. Then what is x? Well, x equal u minus 1, right? So we're going to substitute u minus 1 here. So what is u minus? So you have u minus 1 square and then u power 100, and then dx, as we saw, dx is equal to du. So we're going to write du here. Now, so if we calculate this one, it could seem a bit tricky, but actually it's not that tricky. So we know this formula from our high school is that u minus 1 whole square is equal to square minus 2u minus 1. That means 1 square multiplied by u power 100, right? And then if we multiply it, we'll have 3 different terms. We'll have, if we multiply u power 100 with u square, we'll have u power 102 minus, we'll have 2 multiplied by u power 101 minus, you'll have u power 100, and then d, right? So now let me just wipe this part, and then we're gonna rearrange this part. So then we're gonna write it individually. We'll have u power 102 du minus, we have u power 101 du minus, we have u power 100, right? Now again, with that standard formula that we know by heart, we can see that we'll have what we'll have here. We'll have u power 102 plus 1, and here we'll have 102 plus 1. Similarly, here we'll have minus multiplied by 2, and you will have u power 102, because 101 plus 1 divided by 102, and here finally on this side we'll have u power 101 over 101, right? So then what we'll have, well, the final answer is, okay, we'll also have c. You have to write c because it's an indefinite integral. We have to write an integration c here. So the final answer we have is that u power 103 and over 103 minus, we'll have u power 102 over, cancel it out, we'll have 51 minus u power 101 over 101 plus c, right? So this is basically the answer. So is it the final answer? Well, not really. I mean, we're done, but we have to do one important thing. We have to substitute the original variable back. So we started in the original problem, the variable is x, but we substituted u to make it easier to solve, to convert it into a standard form so that we can solve it quickly. But in the final answer, we have to substitute it back. So the final answer would be something like, wipe it out again. So we're gonna substitute the final answer here. So final variable, original variable to the answer. Final answer will be something like, what is u? U is 1 plus x. 1 plus x or 103, and then 103 minus 1 plus x power 102 over 51 minus u power 101 over 101 plus c. This is the final answer. Okay, as you can see, that answer is very complicated, and if we, I'm not sure whether it's possible to solve it in different way. Probably it's possible to solve by applying a different integration technique, but as you saw, it's way easier if we use integration by substitution. Let's have a look at a final example. Let's have a look at this example right over here. So again, we'll try to use integration by substitution technique. Now the tricky part, as I said earlier, the tricky part is to be able to understand what to substitute u with. So basically we're going to substitute the variable u with some function here, something here, but we have to understand that how we can convert it to that form, like the form that you wanted, desired form, f of g of x, multiplied by this form. So we have to, the tricky part is to understand what to substitute g of x with. So what to assume gx to be, So gx is basically u. Gx and u are the same thing, because we're substituting u with g of x. So the tricky part is to understand like what to assume gx to be in the function. So in case of this example, if you, let's say, some of you may be thinking about substituting u to be like with this function. I mean, assuming g of x to be this one. So assuming g of x to be this one and then substituting it with u. The problem is that if you do that, you will not be able to solve it. It will be probably, I'm not sure whether you can do it this way or not, but it's very complicated. So what you have to do is that we are going to do a bit of trick here. We are going to first rewrite the function in a different way, rewrite the integrand in a different way. E power x, we're going to write it as 1 minus e power ax and then square. This is the trick, so we're going to do it right over here. And then we are going to assume ex to be u. So we're going to substitute u with u of x. We're going to write let u to be u of x. If u is u of x, then what will be du? Well, we're going to take a derivative. We'll have du dx, and we know the differentiation or derivative of e of x is always e of x. So then we have du to be e power x multiplied by dx. So we have this one to be du. So then now we have u to be u equal to e of x, and then du equal e of x multiplied by d of x. So I'm going to substitute this back into the original equation, and let's see what we have right over here. If we do this, well, we have, so e of x dx, we saw that e of x dx equal to du, and then this one is root over 1 minus e power x is equal to u, so we'll have u square, right? Now I'm not sure whether it seems familiar to you or not, but it seems very familiar to me. This is one of the standard integral that you have to memorize, that you have to know by heart, and this basically is equal to, this equals to sine inverse u plus c, right? Plus c, because c is the integration constant. So this is one of the standard integral that we know. So we converted the original integral to a standard integral, and we have this answer. Now we have to substitute the original variable x. We'll have sine inverse, what was u? E power x. And this is the final answer. This is the integration that you wanted. Okay. So yeah, as you can see, like by using this technique, by using integration or substitution technique, we can solve a lot of really tricky looking integral in a very simple way, right? So yeah, what I'll do is that I will attach a PDF in the description box below, and there will be some integration problem, and you can try to solve them by yourself, by using integration or substitution technique. I mean, it should be easier for you because you already know which technique to apply. Because normally when you face an integral, practical integral problem, you will not be sure which integral technique to apply, because there are so many different techniques of solving integration. You will not be sure normally like which technique to use, but here we already know that you're gonna have to use integration by substitution. So try to practice them, and then you can try to comment below like what are your answers. All right. So yeah, that's basically it. Thank you so much for watching, and I'll see you in the next video.